In this video, I will give you a conceptual idea of how definite integral comes about. Suppose we are interested to find the area bounded by a function from a to b like this. As you can see from the three examples here, the areas are easy to find. In the first example, if the function is a constant, which gives me a horizontal graph, the area under it from a to b is simply a rectangle. However, if the function is linear like this or like this, which gives me a sloping straight line graph, the area under it from a to b could be a triangle, or in this case, a trapezium. But both of these can be easily found. But what if the function gives a curved graph? Then how do we find the area under the curve from a to b? So we will now look at the problem of finding the area from a to b when the graph of the function fx is curved. So the actual area we want to find is in gray here, denoted by r. Mathematician Bernard Riemann decided to divide the area r into n subintervals like this. So we have the first subinterval here, the second subinterval here, all the way until the last subinterval here, the nth subinterval is here. So there are n subintervals altogether. Let's now label the endpoints of these subintervals. The start of the interval, let's call it x0. The end of the interval, let's call it xn. And in the middle, we have x1 to xn minus 1. So these numerical values representing the subintervals form the collection of values called the partition of the interval from a to b. Furthermore, the distance of each subinterval, or width, is actually delta x. So in the first subinterval, you can see that delta x, the width, is actually x1 minus x0. In the second subinterval, we can also see that the width is x2 minus x1. So in this scenario, we have the width being equal for the subintervals. So remember that the problem here is to find the gray area denoted by r. Riemann decided to use rectangles or fundamental strips, each with width delta x, to cover the gray area. So the area of the rectangles in red is trying to approximate the actual area which is in gray. And also Riemann is thinking that any excess area created by this rectangle will offset this gray part which the rectangle failed to cover. In the same way, if you look at this rectangle, any excess that the rectangle cover can offset this gray area which the rectangle failed to cover. Riemann decided to use rectangles because areas of rectangles are easy to compute. Let us look at the first rectangle here. As you can see, the first rectangle intersects the curve at this point. So let me find the coordinate of this point. If we call the x-coordinate of this point x1 star, then we can substitute the value of x1 star into the function to get the y-coordinate, which is fx1 star. So this tells me that in this rectangle, the width of the rectangle is delta x, whereas the height of the rectangle is given by fx1 star. So since area of a rectangle is width times height, then the area of the first rectangle is simply f of x1 star multiplied to delta x. Now let's see if you can try to find the area of the second rectangle. Looking at the second rectangle, it intersects the curve y equals to fx at this point. So let's find the coordinate of this point. Let's call the x-coordinate x2 star. Then I can simply substitute x2 star into the function and get the y-coordinate to be f of x2 star. Hence for this second rectangle, the width of the rectangle is delta x and the height is f of x2 star. So area of the second rectangle is the height multiplied to the width. So if this goes on, we can actually find the area of each rectangle. How many rectangles are there altogether here? Since there are n subintervals, then there are n rectangles here or n fundamental strips. So I will be able to find the area of n rectangles. In general, the area of the kth rectangle following the pattern will be the x-coordinate of the kth rectangle substituted into the function to get the y-coordinate of the kth rectangle. This will give me the height, multiplied to the width, which is delta x uniformly throughout in this case. So recall that actually we are trying to find the area in gray, and we are taking the red color rectangles as an approximation. So we can say that the area R, which is in gray, is approximately to sum the area of all the red rectangles. Now this is at best an approximation. To improve this approximation, the rectangles has to be thinner, which means that delta x has to approach 0. And if the width of the rectangle is smaller, it also means that the number of subintervals or the number of rectangles will increase. Hence, the approximation of this gray area R can be improved as the number of fundamental strips or the number of rectangles gets larger towards infinity. This means that we can take limit of this sum, which we call Riemann sum, in honor of Riemann. And if the limit exists and is finite, we then say that the function f here is Riemann integrable. So as n goes to infinity and this Riemann sum approaches the value L, then the value of L can be denoted in this way, and this is called the definite integral of the function f from x equals to a to x equals to b. Hence, as the number of subinterval n becomes larger and larger, we notice that this summation notation becomes this integral notation. And this delta x notation becomes this dx notation. And this fx notation becomes this fx notation. Such changes is due to the limiting condition as n goes towards infinity. This is how the definite integral comes about.